really, really excited to bring two absolutely wonderful resources that really demonstrate the power of relationships in education. We all know that it's super essential to reach out and lean on those around you as a teacher, but it's also always good to see what resources are out there and what you can get involved in for your classroom, for your building, for your students. So that's kind of what we are looking at today. We are bringing to you two individuals, Luis Jimenez. He is an advanced electronics teacher at Boucher High School in the Toledo, Ohio area. And he has been working with Gerald Voltz for 10 years now, I think you said?
7.
7 years, so nearly 10 years. So we've got Gerald Voltz here, who is an education program specialist at NASA Glenn Research Center in the Office of STEM Engagement. And if you haven't, please take the time to go check out the NASA Office of STEM Engagement. It is just an absolute treasure trove of every resource that you could ever imagine for a teacher. And it's not just space and astronomy, right? There we go. We had an astronomy teacher at my school that I worked at, and we would tease him all the time and ask him about our horoscopes. He did not appreciate it. I will absolutely make sure to share the link to those resources in just a moment after we get started. But Jerry was I believe you said you were an educator, and then you kind of transitioned into the contractor stage, and now you are an official government employee working to bring, again, amazing resources to educators in the Ohio area, but again, doing a lot of work to bring and make those resources accessible nationwide. So is there anything additional that you two would like to provide before we begin, or are we ready to go?
I think I'm ready to go.
All right, take it away, Jerry.
Okay. Well, thanks, Ashlyn. Again, I'm Jerry Voltz from NASA Glenn Research Center. I'm an activity manager for 2 projects. One of them is the high school, NASA Glenn High School Capstones, and another one, actually there's 2 more. We have Make It NASA activities that, feature maker type activities, and we have engineering design challenges that are developed to teach Ohio teachers the engineering design process that I believe Lewis is going to talk about after my presentation. So I know the title of the workshop is Robotics, and we will certainly get to that, but Ashlyn thought it would probably be a good idea to talk about the other capstones as well. So I'll save our robotics-oriented capstone for last, and that'll be a nice transition to Lewis. So to begin, just an overview. We offer, we're always trying to find ways to engage students into the research and development that's done at NASA Glenn Research Center. Sometimes that is a very formidable task because research and development isn't always thought of as being exciting. It's not like we're at mission control at Johnson Space Center, where we're doing robotics missions out of the Jet Propulsion Lab and those types of things. But we do have these capstones in Ohio. Ohio teachers were looking for capstone projects for their juniors and seniors to participate in. However, some teachers actually modified some of these so they're freshmen and sophomores. So we just instead of senior capstone projects, we just changed it to high school capstones. So we have the following capstones that relates to research that's done at NASA Glenn. And one thing I want to mention, we did have a workshop for one of our new engineering design challenges. It's a cryogenics activity called Keep It Cool. And everyone, again, was focused on the space part. And oftentimes people forget the first A in NASA is aeronautics. So it's the National Aeronautics and Space Administration. So we do a lot of aeronautics research. One of those things that we do is acoustic damping. That's basically reducing noise pollutions of jet engines, which is pretty important, especially if you live near an airport, as I do. and as many Clevelanders do. We have another capstone in hydrology, power management and distribution. That's basically all of the electronic systems aboard the International Space Station and Gateway, which is part of our Artemis mission to go back to the moon and beyond. We have a Materials International Space Station experiment. This is a highly selective one, and it's really restricted to people that can drive on the lab where the kids do actual experiments. Remote sensing of harmful algal blooms. You'll see some of Lewis's students in some of the slides I have for that. And then finally, simulated lunar operations. That's where we have our application of robotics in using a robot test vehicle to test wheels. Usually our capstones, they begin in August. However, we do have some capstones running this summer with some Cleveland metropolitan schools. And we offer virtual training in October, usually about 5 hours. And it's really mandatory for safety considerations that the mentors that will be working in person with the students will have to go through this training. We have a kickoff meeting with our subject matter experts, which really consist of scientists and engineers. And then we have bi-weekly meetings. So every 2 weeks, I will meet with all of our participating organizations. Right now, we're currently in Ohio. However, I've been told that we're going to try to expand this nationally. So hopefully I'll get a little bit of support. So it's just not me doing these bi-week. Although I would love to do that as a former teacher. I would love to do that. I get to interact with students and I don't have to grade homework. That's wonderful. So for me anyway. So then we have a midpoint check-in with a subject matter expert connection. Usually at the kickoff meeting, students don't really know enough about the project to ask any questions. But after they've worked on it a little bit, then they start to have some specific questions about their capstones. And then we have culminating events in April. And the reason why we choose April is because May is a huge testing month. And we discovered that within the first 2 years of this project that May, even though it's a nice time to do culminating events, it's hard to schedule around people, taking AP tests and graduation tests requirements and things like that. Okay, so moving along, we'll start out with acoustic damping. So many students like this. This is actually our most popular capstone, which it surprises me, but it doesn't surprise me. I think young people today are very environmentally conscious. And one of the first schools I worked with, the Akron National Inventors Hall of Fame High School in Akron, he did this great job with the acoustic damping. And I said, oh, so, you think you might want to work at NASA as a acoustic damping scientist? And he said, no, I was just more interested in the noise pollution aspect of it. I didn't particularly, want to work for NASA or anything like that. But I think a lot of students are very interested in this. So we've had to really make adjustments with COVID because usually this was a face-to-face activity, but we figured out a way to make this virtual. So I'm going to go ahead and and another thing, high school physics teachers really like this because it talks about standing waves, incident and reflected waves, and resonant frequencies, and so those are things that are usually covered in physics, and it's a great application. Like, where is this stuff ever used? So going to the next slide. So what you see here on the left is a 3D image or 3D sample. And we have this impedance tube. It's basically 2 inches in diameter. And the test sample is about 2 inches high. This is designed in Tinkercad, but it can be in any CAD drawing, but Tinkercad's free. So that's the right price for many of our schools that we work with. And then what you see here is a student impedance tube. So it's not really If we were to get more exact, we would have 2 microphones here instead of 1. But basically, we have a signal generator here that basically outputs a signal to this op amp, and so we have a lot of basic electronics going on in here. And then that op amp will output a signal to a speaker. It will send out an incident wave, and then there's a brass backing here, and this is the test section right here where the student designs will go. And then what happens is we have an oscilloscope that measures a peak-to-peak voltage, and then what happens is once that peak-to-peak voltage, we measure the difference of that, and so if we do it without the sample for a baseline. So let's say it's 900 millivolts peak to peak. We put the sample in, it might be 700 millivolts. So we know that energy is being absorbed. And again, we want absorption. We don't want reflection off of the sample. And then here are some examples of some of the samples that we've done. So they could either be 3D printed like this one here, or it could be, or you can make them out of, straws or craft rolls, or craft paper, craft paper, things like that. Okay, hydrology. This is basically, some of you may be familiar with the NASA GLOBE project. That's global learning and observations to benefit the environment. It's basically a citizen science. It's a K through 12 project, and we focus on the more challenging protocols where you'll conduct studies of dissolved oxygen, nitrates, pH levels, and things like that to determine the health of the local water resources and watersheds. Now in Toledo, some of you, it's been some years now, but they actually had harmful algal blooms take over they infiltrated into the water system, and they were without water for at least a month. So they had to have all that potable water shipped in. So they're very interested in runoff, nitrate runoff from farmers' fields. And so what they did with this project is they analyzed the steepness of the slopes, the drainage slopes from the farm fields, to see if the slope is more gradual, does it prevent more nitrates from entering into the watershed? So they did this nice poster board presentation, which was really, really impressive. The students at the Toledo, I think it's the Toledo Airspace, and that's maritime. Natural sciences did this one. Okay. This one, I'll just talk briefly about this. This is the actual experiment. So some people will say, we do experiments on the International Space Station, and sometimes the International Space Station itself is the experiment. Particularly, how do the materials that make up the space station handle the radiation? Even though we know the International Space Station is safely within the Van Allen belts, we still get significant radiation that we can test to see how different materials hold up with that. So here, students, this is a very, it's only open to maybe a couple of students, and this will go for a couple of years, where this little packet of materials then will be shipped back down, and the students will actually perform the testing to see the various levels of degradation of the materials. So right now we have students from Hathaway Brown School in Ohio, and they come on the lab to do this. Power management and distribution. So basically we're looking to, instead of manually controlling our power systems, to automate them. So basically we have solar arrays that charged with lithium ion batteries, and I think that they were nickel cadmium, and they just did that replacement, I think a couple of months ago, where they replaced all of the nickel cadmium with lithium ion battery packs. And so then what we have here is, again, Tinkercad has a circuit application where they can build their circuit, and they learn the basic electronics of PNP resistors. So these are students that maybe they're in an AP track and they're not in a vocational track. They get an opportunity to learn just some very fundamental electronics. And then they can not only design their circuit on Tinkercad circuits or any other circuit application that they have, then they could build it up and test it, which they really enjoy that. And then excuse me for just 1 minute. That's my little alarm. Make sure I stay on track. Okay, remote sensing of harmful algal blooms. We talked a little bit about this in our globe hydrology. This one actually was a remote sensing. We have a multi-spectrometer that can detect hundreds of colors. And what they do is they try to detect it just by the color of the algae to see if it's harmful or not. So what we do, and Lewis he's been working on this for a while. What this kind of evolved into is not only to detect the algae, but then they wanted to have a water capture device that you see on the right, and then and it'll capture water about a foot underneath the surface. This was this had the interest of a lot of people that do that ground testing, because the way they do it right now, they just take a styrofoam cup on the end of a stick and they row a boat out there, and they get their algae. But the boat churns everything up, and you just wonder about the test that you're getting. With a drone, you can be far enough away from the surface that you can effectively get a better water sample without disturbing the water. So that's always a fun one for students to work on, and they have a different design every year. So this is just one. This was my most favorite so far. And then finally, I'm going to turn it over to Lewis after this one. We have our simulated lunar operations, and this is our simulated lunar operations lab. This is our lunar test bed. We also have a Mars test bed where we test wheels, we test excavation equipment, and anything that we're going to use up on the moon. So we had this new Viper testing where this robot's going to look for water ice. So the Viper robot was here testing the wheels to make sure that it could traverse around the lunar regolith. So this, again, it's a simulated material. It's not actual lunar regolith, but under a microscope, the shape of the sand matches that, and for traction purposes, it's pretty good. So we're pretty happy about this one. And then this is where we have our robotics. So we have motors that are geared at 75 to 1. And then this is our little simulation of a simulated lunar operations lab. So it's about 4 foot by 8 foot. It's got a little car jack to make the tilt adjustable. And then we add weights to these to see how much weight they can go up a 14-degree slope, which is a pretty significant slope. You wouldn't think it would be, but it is. So anyway, and then we have this. Now they use Vex Robotics, this particular team, but usually we'll control this with an Arduino and we'll have a Bluetooth receiver transmitter, and we can control it with our smartphones. So, control it going up and down, left and right, things like that. And then you can see the wheels here are 3D printed. So what we did, again, for this capstone is we had the students design their wheels, 3D print them, and then I have a couple of 3D printers in my basement. So we printed out the wheels, and then we tested it basically in my garage because we couldn't get access to the lab because of the COVID restrictions. So that's about it. So that's and then I have our partnership with Toledo. So Lewis, I'm going to hand it off to you. I'm going to, I have another short meeting for 10 minutes that I just have to give a little bit of a presentation. I won't log off. I'll log on another computer and I will be right back. So Lewis, I'm going to hand it off to you.
Thank you, Jerry.
Oh, I guess I'm supposed to go to the thanks slide. There you go. Okay.
Thanks, Jerry.
Okay.
Good afternoon, everyone. My name is Luis Jimenez. I've been a teacher in Toledo, Bowser High School, for the last 20 years. I do have some experience in the real world, though. I am a Navy veteran. I joined in 1969. Yeah, don't ask. Um, yes, I am older than I look. And I'm also retired from a company you probably heard of, General Electric Aerospace. I'm very proud of that, by the way. I learned a lot there. I learned where SMART goals come from. Probably about 100 years ago, General Electric actually defined the concept. I have the books to prove it. So, as a sailor, one of the first lessons I learned was that, not everything you do is going to make a difference. Sometimes you'll make a small difference, sometimes you'll make a big difference. It just depends on how much you're willing to invest. And I learned at an early age that a smooth sea never made a great sailor. Franklin Delano Roosevelt said that. I probably lived it, but he said it. This is one of the first things I learned in my engineering courses at General Electric Aerospace. Thank you. In my courses at GE, one of the first lessons I learned, my engineering courses, was to every principle, there is both a process, which is the road or the path, and an effect, which is the destination or the outcome. And I have tried to focus on both of those areas with my students to make sure that they understood that the process is just as important as the outcome. Sometimes even more so, because the process teaches you the difference between experience and education. I learned this at an early age. I don't know what I did wrong. My father said, do you understand the difference between education and experience? And I said, Dad, I'm 9 years old. Not really, no. He said, listen carefully because this will help you for the rest of your life. And I said, okay, I'm listening. He said, education is what you get when you read the fine print. And I said, okay. He said, experience is what you get when you don't. I didn't understand that. I was 9 years old. I understand that now. I'm a lot older. Yeah, the students have a problem sometimes saying Jimenez. And I say, that's fine. Just call me what they called me in the Navy. And they go, what's that? They just referred to me as Menace. I have no idea why. And then I just kind of used it and have gone with it. Menace of the Dark Right, the Phantom Menace. Hello from India. Awesome. Okay, we're going to go through the NASA engineering process. I'm going to go through this kind of quickly, and then I'm going to show you a video, okay? Because I would rather focus on the video as opposed to the PowerPoints. I know people get tired of PowerPoints, okay? This is the NASA engineering design process as taught by me. Glenn Research. It has been an honor and a privilege to be associated with NASA and with Jerry for the last 7 years. We have developed a tremendous working relationship, and it's taught me a lot. It really has. It's helped me modify a lot of things in my class. Hopefully, this will help you modify some of the things in your class. Okay, this is the NASA engineering design process. Now, in K through 8, and this is how it was originally introduced to me. I developed a term for it. It's called AIPCES. AIPCES. AIPCEIS. It's ask, imagine, plan, create, experiment, improve, and share. Hello from India. Awesome. When I began teaching the engineering design process, I wanted to make it easy for my students to understand. And I knew about the NASA Jet Propulsion Lab engineering design process, which was designed for high school, okay? But as I began to research the two and research what was taught in K through 8, which is APSES, ask, imagine, plan, create, experiment, improve, and share, I began to realize that there really isn't any difference between the K through 8 and what they were teaching in high school. And an engineering friend of mine said, well, how can you reconcile those two? And I said, you mean what is the difference? He said, yes. I said, well, at the JPL, the Jet Propulsion Labs, he says, yes. I said, they just use bigger words. And he started laughing. He said, it's the same thing? I said, it's exactly the same thing. I said, they just use bigger words. So, APSES, ask, imagine, plan, create, experiment, improve, and share. Now, there is this things out there, they're called smart cars. And these are going to be the ultimate programmable remote control robots, okay? And they use what is referred to as computational thinking. And since I have gone through the training, which was administered by the National Science Foundation through the University of Toledo, and Bowser High School was one of the first 2 schools in the nation to go through this smart car training. And I was introduced to computational thinking, and there's 4 parts. There's 4 parts. And the 4 parts are decomposition, pattern recognition, algorithm design, and abstraction. Now, decomposition is taking the problem or the project and breaking it down into its component parts. You're going to take it apart. You're going to turn it into parts. Pattern recognition is your database of information. So in decomposition, you would be identifying the problem. And one of the ways you will identify the problem is you're going to ask. And you're going to ask what? What do you ask? Well, and this is something I borrowed from Rudyard Kipling. And if you're not familiar with the name Rudyard Kipling, he wrote the Jungle Book, but he also wrote a lot of short stories and poems. And one of his poems, I borrowed it to develop this. I have 7 honest serving men. They taught me all I knew. What if and when and why, how and where and who. And I have my students, when they start asking, well, what do I look for? I go, you look for answers to the 7 questions. I have 7 honest serving men. They taught me all I knew. What if and when and why, how and where and who. Identify the problem, analysis, okay? Decomposition. The next is you're going to brainstorm, you're going to imagine. Younger people can imagine a lot more things than older people can because they're not restricted by reality. They're not restricted by experience. There's lots of things that they can come up with that are probably not going to work, but they're going to come up with it anyway. So imagination, ideas, brainstorm, doing the research. Reality check. Reality check, reality check. This is where you are going to actually look at what have you determined through decomposition and pattern recognition. What have you determined? Is this going to work? Are these ideas going to work? Okay, we're going to select which ideas are going to go forward and which ones are not going to go forward, okay? And we're going to use something called the triple constraint, which is a business concept. It has to do with the quality of anything. And it has performance at the top, and you have time over here, and you've got cost over here, okay? Okay, now, the constraint on performance is specifications. This has to do with the quality of anything, okay? Now, specifications are like options on a car. Okay, well, time, the constraint on time is always going to be schedule. We all have a schedule for things. We only have so much time to give this presentation, okay? The constraint on cost is always going to be budget, always going to be budget. And these three things, performance, time, and cost, they have to do with the quality of anything. And that's one of the things I have them roll into the reality check along with their answers to the 7 questions. Now, the plan. Most people don't plan to fail, they just fail to plan. And you need to develop a plan of action and milestones. This is actually the big picture concept, okay? You can put together a plan of action and milestones in a matter of minutes, okay? Then you can flesh it out, but it's actually a timeline. It's a start, it's a finish. You've taken your project and through decomposition, you've broken it out into its component parts. You've developed some information about it through pattern recognition and getting answers to the 7 questions. And this is algorithm design, okay? And this algorithm design is actually a list of steps on how to actually accomplish your plan. This is going to be your list of steps, and this list of steps in algorithm design, this is called a POP, a plan of procedures. It's going to be a list of steps, and your plan of procedures always has with it a parts list. Has a parts list. There's going to be a parts list, and then there's going to be a list of steps on how to actually accomplish this task, this project, or solve this problem. And you're going to do it through using SMART goals. Remember we talked about SMART goals, General Electric? Yeah. You want to make your project, everyone who's working on it has a SMART goal. It's going to be specific, measurable, achievable, results-oriented, and time-constrained. And if you never worked with a plan of action and milestones or SMART goals, or have a POP, most people don't plan to fail, they just fail to what? Fail to plan. Okay, so next is going to be create. This is where you're going to use your POP, your plan of procedure. This is where you're going to start developing your theory of operation. And then you're going to experiment. You're going to test and evaluate this. You're going to optimize the design, refine the design. This is abstraction. You're going to find out what works and what doesn't work. And then you're going to take all that information that you've designed, okay, and you've developed, and through abstraction, you're going to come up with one, what they refer to as one best solution that can move forward, that can be added to your pattern recognition. So next time this happens, or next time you have a problem like this or a situation like this, you're going to be able to go through it a lot more efficiently and effectively. And the last thing is everybody can do this, okay? It's called share. Sharing. What do we have out there? Social media. People share too much information. The way we share in the classroom is through the digital video portfolio, which I will go over here in a moment, okay? The build is project design. That is a part of APSES. Now, ask, imagine, plan, create, experiment, improve, and share. APSES. That's K through 8. Okay, at the NASA Jet Propulsion Labs through high school, here's what they use. Identify, brainstorm, select, build, test and evaluate, optimize the design, and share. It's exactly the same thing. All they did was use bigger words. Ask the 7 questions. I have 7 honest surveymen. They taught me all I knew. What if and when and why, how and where and who. Imagine, brainstorm, pattern recognition. Develop your database of information. What if? What if, what if? Reality check. Solution more challenging than realistic? Yeah. How many times have people selected things or ways to go or designs that were more challenging than realistic? And here's the triple constraint. Plan of action and milestones. Right here is a plan of action and milestones. This is your project or your task or whatever it is. I've broken it out into its component parts, and right down here is a timeline, okay? Right down here is a timeline. And you can use seconds, minutes, hours, days, years. Build a model or a prototype. Create. This was our first fully programmable remote control robot, 2014, and we used Raspberry Pi. I was very proud of it. It took us a while to do it because we didn't know anything about programming, and we were building a robot. Test and evaluate. Testing. Very important. Optimize the design. This is abstraction. You're going to take what you've learned and you're going to go over it and you're going to refine it. You're going to take out things that are unnecessary and then see if you can make it more effective and more efficient for next time you go through this process. Share the solution, digital video portfolio. The engineering design process. APSES. You should say it to yourself. APSES. There's two things that I also try and make sure that people understand in my classroom, especially when I'm teaching them, is writing. Writing is repetition. Repetition is retention. Retention is remembering, and remembering is memory. And then there's another part to that. It's like two sides of a coin. Reciting. Reciting is repetition. Repetition is retention. Retention is remembering, and remembering is memory. And my students go, well, I can't remember that. I go, well, write it down. So this is how I teach my classes. This is how I teach my advanced electronics classes. And I have incorporated the engineering design concept into what they do, and then I made this with a program called Animoto, and you can actually add your own video to it. I wanted to show you this program because it's absolutely free. And it is a very effective program for putting together presentations like this and teaching in the classroom. And it works very well, as you just saw. Another program that you should probably be aware of if you haven't used it yet for collaboration is called Google Jamboard. And this has so many possibilities. And they want you to purchase it. You don't have to purchase it to do what I just showed you, okay? And again, like I said, as Jerry said earlier about Tinkercad from Adobe, it's got the best price. It's absolutely free. Now there will be a little watermark in the corner, but everything else works perfectly fine. Just so you know, that also was made with Animoto, and all those pictures you saw and all the video that you saw are absolutely free on the web. So it's unlimited what you can do. Unlimited what you can do. What are some standard and essential tools, materials for a STEM lab? Basic. It depends on what type of STEM you would be interested in going into. This has to do with robotics, fully programmable remote control robots, and the programming part of it is just and can be just as exciting as the actual building of the robots themselves. It's the creativity that makes us different. I will give you my vision mission statement, and then turn it over to Jerry. I firmly believe that career and technical education is at the heart of our high-tech, high-skill global economy. And for America to remain economically competitive, her next generation of leaders, the students of today, must continue to develop and improve those creativity, communication and collaboration, critical reasoning, and computational thinking skills that will help keep them and us the most powerful and productive in the world. Hi, Jerry. Welcome back.
Hi, Louis.
Is there anything else you wanted to add?
No, I think that just about covers it. I don't know if there's any questions that we can answer at this time.
And Emily has a question. Emily, what kind of STEM are you interested in? Excellent. There is a program called GoPyGo. So actually, it's a website. Okay. I think that's it. GoPyGo.com. And that deals with robotic smart cars, small ones, and it uses Blocky. The programming language developed by Google, and it is an excellent way to get started. Okay, you could also research parallax. The program for learning software development or programming, I would recommend CoderZ. It's an awesome way to start. It really is. And yes, students actually building things, getting their hands in there. Every project that we work on has 8 parts to it. It's got a pictorial. Since I do electronics, okay, I have them building things. I have them. It's a pictorial, schematic, artwork, theory of operation. They build a prototype or do a simulation. Then they do their POP, their plan of procedure, which is their list of steps. They actually build a project that works. That's the 7th part. And then the 8th part is the digital video portfolio that I just showed you the video on, which is actually fun because you can actually do a digital video portfolio in PowerPoint and then turn it into a video through PowerPoint. Okay, and one of the basics I tell my students is the PowerPoint, your digital video portfolio has to have text, context sensitive text, pictures, music, and video. And for those of you that are not sure of where to get information on STEM or how to get started, my suggestion would be to go to nasa.gov. That's what I did 7 years ago because I didn't know how to get started with robotics or drones or the engineering design process, which I have transferred to my students. And if you took a look at the digital video portfolio, it is a thinly veiled scientific research report so that when they go to college and somebody says, well, we have to do a scientific research paper, they will already have done several of those in my classroom in the form of digital video portfolios.
We do have some questions coming in. Mr. Jimenez, they're asking if you have any video portfolios created by your students that you would be able to share, and we can do that afterwards.
Yes.
But
yes.
People are asking you for resources too. They would love a PDF of your process. They're very impressed by it. We have another question. How do you decide when you have tested enough? By Brad. He's curious about that process.
Okay. So what do you mean by testing enough? The engineering design process is basically, if you stop and think about it, it moves towards a competition, which drives, well, basically that and capitalism drive everything, right? But competition is very important. Our last capstone with Jerry that we just completed, we competed against two different schools who had 3D printers and we did not. So I told my students, I said, well, we're going to focus on the engineering design process and get answers to 7 questions. And hopefully, with the research that we've done, we will have a tire that will beat the tires from the other schools. And that's exactly what happened. So I was very proud of my team that did that. And we used, because we didn't have a 3D printer, we used the engineering design process to drive our success. So how do you know when you've tested enough? I don't know if you ever know when you've tested enough, but you do the best that you can with the tools that you have. And one of the tools that I have found that has really driven my students over the years has been the engineering design process. I have students who have become electrical engineers, mechanical engineers. I have students who have gone into programming. I have a student who is now a friend of mine who actually got into the University of Tokyo in Japan for electrical engineering.
My goodness.
So you don't know what difference the things that you teach are going to make until you see the difference that it makes in your students.
So Emily also would like to know how much time you end up spending on a project such as you've shown. Is this a whole year process, or I mean, how much classroom time are you taking to accomplish this?
They are longitudinal projects. We had roughly, because of the pandemic, we had about 2 months to actually work on the project. Okay, so we didn't have a whole lot of time, but what we did was we developed a plan of action and milestones, and we divided it up through, decomposition. We divided the project up, and then every person on the team had a SMART goal, making it specific, measurable, achievable, results-oriented, and time constrained. And then we had a team leader, and he did a fantastic job. Naj did a fantastic job of keeping everyone on track and on task. And then when we sent our specification information to Jerry, printed out the tires, did the testing, and our tire design won the competition.
That's amazing. So we had a few questions about this earlier, and I'd love for Jerry to speak on this. You yourself were a classroom teacher. At what point, how would you take this to an elementary classroom? The concepts and the processes that we've been talking about today, we've been very, very high school focused because that is where a lot of this can happen. But there's no reason we can't take this to K through 3. So how would you kind of go about doing that?
So we have a program. It's called NASA BEST. It's Beginning Engineering, Science, and Technology. And they have grade bands. They have a K4 grade band, and then they have a 5 through 8 grade band. And so for the K4, they don't focus on all of the aspects of the engineering design process. They just hone in on a couple of them because of the audience that we're dealing with. And then on the middle school, then we'll incorporate a couple of the other principles of the engineering design process. So then by the time you get into high school, you're doing the full process. So they just might have the activities actually build on one another. So they might have a green propellant activity. How can we use biodegradable materials to propel a quote rocket ship across the room on a fish wire, basically. And so they experiment with different materials. And then the middle school, it'll be the exact same activity. It'll just be more advanced and more in depth. So they might add more materials and more parts of that. So if you just Google NASA Best, that's probably our best bet. We also have NASA at Home, and they are also these are activities that students can do at home. Actually, I should put that in the chat box too. And this came out right when the pandemic hit. They put this website up, and it was on Good Morning America, and everyone was, oh yay, So and they have some good activities there as well.
Sorry. Wow. Yeah, no, there's an absolute wealth of resources, and I really encourage everyone who is here to prowl the NASA various websites to see what they can glean from it. In addition to not being afraid to reach out to your local or your nearest NASA research center to see what kind of resources they have and what kind of programs that they're doing that you might not know about, like Jerry and his wonderful Capstone project, in addition to the other projects that I'm sure he does. All right. Any other questions? We have one more question, and this might be for Jerry and Luis. Any knowledge of investments in STEM or student initiatives or projects? So any kind of funding sources that you might be familiar with that you could share if someone is trying to, like Emily, perhaps trying to kind of get started with a STEM lab in their building. Do you know of anywhere that they could go easily to see if they could acquire funds for that?
Yeah, I mean, we did have a partnership with 21 CCLC, but I think with the Department of Education, but I think that funding is going away, but maybe it might be reinstated. So NASA does have a partnership with them, and they do have engineering design challenges. Outside of that, unfortunately, the only funding opportunity that I'm aware of is that we have winter and summer solicitations, and they'll be on the NASA Glenn Office of STEM Engagement website, where we will assist with providing materials. So we provide a 2-day virtual training. So we have 2 hours of training and a 2-hour break, 2 more hours, and then we take a day off so people can work on their projects independently, and then we reconvene on the 3rd day to show off. Everyone shows off what they did, which is a lot of fun. And the teachers learn from each other. They probably learn more from each other than they do. I mean, we just get them started, and then once that happens, then watching the creative solutions is always fun. So if you're in Ohio school, and we're particularly focused. I mean, we're open to everybody. We do have a focus on those schools that serve populations that are underserved in STEM. So that would be either by race or gender, or actually urban or rural. We find those populations are generally underserved.
Excellent. And not excellent, but I do know, so something that CoderZ is offering right now is Amazon, actually through a partnership with us, is offering, they are underwriting CoderZ for 6 months for any Title I district. So that is something that could be used as a resource to bring some STEM, at least kind of a toe dip into it for some districts. Something else that we have right now that is totally free is the Amazon Cyber Robotics Challenge, which makes for a really wonderful 1-week kind of experience with your students that involves a virtual field trip with Amazon engineers at the end of it. It's free, it's fun, and it is a wonderful kind of first week of school kickoff activity to get your kids on their devices and make sure. CoderZ, is currently being underwritten by Amazon for 6 months for anybody at a Title I school. So we'd be happy to be a part of your building. Louise, go ahead.
Yes, I got my students involved with CoderZ, and at first they didn't really know what it was, but as soon as they started getting involved with it, they really got into it, and it is fun and it's challenging, and it you start out slow, but after a while you start realizing that as you get smarter, it gets smarter, and it challenges you even more. So it really does teach you the basics of programming.
That's wonderful. It's a really wonderful, I don't know if Jerry stopped talking. It is a really wonderful kind of way to really get it into your classroom. Here's that information slide there. Yeah, we're here to bring resources to everyone. I have one more question for Jerry. I would love to know kind of what's your favorite project that you have done in your position? What's your favorite thing that you have done with students or with teachers that really has made a difference in your mind?
Yeah, I would say that some of our select schools that we work with to develop engineering design challenges and capstones, that's always fun, because the students know they're contributing to something that's going to be used in the future. Also mentoring college students in our Office of STEM Engagement. That's also a lot of fun for me as well. So, developing the content, seeing what works, seeing what doesn't work. Sometimes I'm just as interested in what doesn't work, than what does. And I think that's important to stress that to people, that you still learn something. You learned what didn't work, so you know not to go down that path. But that maybe if technology changes, that path might be something you can revisit at another time. So, yeah. So just the developing and watching just watching the ideas that the kids come up with, and things that I would have imagined. And by the way, for the scientists and engineers, that's why they like being involved in these capstones and these engineering design challenges, because they'll see a different approach, because even they can get locked into a certain way of thinking. So it keeps their perspective fresh, watching what the students come up with.
It's so valuable to see them with no restrictions and no right answer too. I think that's something that's so powerful. I remember in my classroom, I was doing a project that was very inquiry and completely, totally open with a class of honor students, and they were just lost because there was no right answer, and they were so frustrated by that. They didn't like it.
Yeah. Well, I have to say, with the engineering design process, which is different than the scientific method, there is a beginning and there is an end. So you eventually have a product, because you want something that someone can use. But it may take you a couple of iterations to get the most effective design. But then at some point, you're putting in a lot of effort for very minute improvements. And so that's when someone said, when do you know when to stop? Yeah. So, if it takes you 36 hours, contact hours to get to a certain point, and you have like 90% efficiency, but now you're taking another 36 hours to go to 91%, maybe that's the time to stop. But,
the asker of that question, Brad, he followed up with thinking about ingenuity. When was it decided that it's ready to launch? That's, I think, the context in which he was trying to assuage that question.
Oh, okay. That was the context. Okay.
Yeah. But that's fair. Like, at what point do you decide, okay, this is good enough, we're going to go?
Yeah. That's a tough one. There's a great video. They talked about the old Mars exploration rovers, And so, these are, you don't buy these rovers off the shelf at Walmart. I mean, these are all things that are especially, and they were doing an impact test on the, on some of the instrumentation, which was like, $5 million. And so the principal investigator is saying, so you're saying it's ready for this test? And the engineer says, well, I don't know if it's ready. We've never done this before. Well, can you give me some odds? Well, I think it's as ready as it's going to be, but I can't really tell you what that is. And the principal, they want to know, because we only have 2 of these. And if it breaks during your test, now we're down to one rover instead of 2. I mean, that rover's done. That mission is over before it even starts. And then they do the test, and they bring this big hammer on a plate to do a vibration test. And he's in the airport. The principal investigator's on his phone. Okay, what's going on? What's going on? And it obviously survived the test because they both launched and they both had successful missions. So that's, you're never going to, and we have these frustrations even in the Office of STEM Engagement. So I'm developing it, and my project manager, he wants to know it's going to work, right? Well, we've never done this before. I'm pretty confident it'll work. I don't want pretty confident. I want to know, well, you don't know. And then even when we implement, we beta tested this thing, our last design challenge. And then no one thought to test styrofoam, because we all thought that was kind of cheating to keep something cool. And then and we had to use warm water as a heat source. We couldn't use a blow dryer because safety said no to that. And so we put the styrofoam in the warm water, just flipped over. We're trying to keep ice cubes from melting, basically, in this engineering design challenge. And it's like, oh my gosh, we had all these people working on it, and no one saw this obvious, problem. And sometimes, you can be so close to it that you're not thinking of the most obvious things, and that all comes out. So then, we improve. So we have to do our own iterations, in the content that we develop. So anyway, enough of that.
Okay, so I think that those are all of the questions that we have from the audience. So thank you all for joining us. Big thank you to Jerry and Luis for taking their time to be with us today. We really appreciate it. And I know I enjoy my time with them. And please come and join us for our next Ed webinar. Somebody asked a question earlier about creating a STEM space or STEM lab in their building. We are going to have the opportunity to speak with the CEO and founders of Grainweevil, which is a agricultural technology robot that came out of a really, really gorgeous rural kind of incubator space that Chad Johnson has developed in his small Nebraska town and has done a really wonderful job with. But he has been taking a mobile makerspace around Nebraska for years, and he has developed a very deep library of resources for educators that is super valuable. So thank you all so much for coming. I hope to see you next month, talking to Chad Johnson and seeing his grain robot. It's very cool.